Test, test.
Hi, Dan.
Hey, good, good.
Hello.
All right, let's see here. So, still about a minute or so. How is everybody?
Good. Snowy and cold here.
Is it?
Yeah, it is. Yeah, we got about 2 feet of snow now.
Oh, really?
Yeah, we do. Yeah.
Is the polar vortex sitting over top of you or something?
Uh, it's just actually most of our weather comes from the West Coast,
Okay.
and so if the rain gets past the mountains, then it really dumps on us.
Mm-hmm.
Where is this at?
This is in Pullman. This is in Washington State. It's in Eastern
Oh.
Washington. It's right near from my window, I can see Oregon and Idaho. So we're right in the southeast corner of the state.
I thought you were talking about the Midwest for a minute, and I'm like, yeah, the Midwest keeps getting beat too.
Yeah, they really do. Yeah.
Your statement was reminiscent of from my house I can see Alaska, so I can see Russia. So
Yeah, that's right. Yeah.
that's what popped into my mind.
Yeah. Actually, the funny thing is the next town over is Moscow.
Oh, really? So
Yeah.
from your house you can see Moscow.
That's
So.
right. Yeah, that's right. Yeah.
Let's see, I'm recording. Okay, we'll give it just a few more seconds. Let me get stuff set up. May have a couple late joiners. The sign. Okay, and share. Okay, good, you're all still there. Okay, so this is lab 4, so we're moving farther out in the universe. Lab 3 was the Galilean Revolution, and where we established the heliocentric model over the geocentric model, measured the mass of a gas giant using Newton's form of Kepler's third. So now we're beginning the cosmic distance ladder. So let's go down to a section here, open up a lab. Lab 4. Okay, have it already open. Okay, reloaded. Okay, so standard stuff at the top as always. The link to one of my TAs giving a pre-lab talk. Then the most important thing that you always have to look for is this note down here saying what observations have to be submitted for the next lab. So lab 4 and lab 5, they all kind of build on each other at this point. Lab 4 is parallax, so that gets us a certain distance out. And then after that, we'll use standard candles in a couple steps to get much farther out. Now, the standard candles that we do are Lyraes, Cepheids, and type 1As. The Lyraes are good for distances kind of within the galaxy, distances to the globular clusters. The Cepheids get us out to the nearby galaxies, and the type 1As get us out to more distant galaxies. And the only Cepheid that you can really see, other than in, say, the local group or Magellan Clouds, with our small telescopes, it's one that Hubble used. And it's a 60-day period Cepheid. So the students really can't observe that over the time scale of one lab to the next, so that is canned. And the type 1A supernova, you never know when they're going to occur. We've discovered lots of them. There are a couple supernova programs running on prompt, so we have good archival data there. So the one thing they can observe is the R Lyrae. So let's put lab 4 aside for a second. I'll load up lab 5 and show you how we put this R Lyrae observation in. Then we'll use it next time. So here we are in lab 5, Cosmic Distance Ladder Part 2, Standard Candles, and observe a globular cluster. So there are in the lab, there are 3 globular clusters for different times of the year. In the northern hemisphere fall, we observe NGC 1261. In the spring, it's 3201. And if you have summer students, they do M28. So there's always going to be one of these available any time of year. And the finding charts and all that will come back to you next time. But let's put in NGC 3201 just as an example. So here's Skynet, optical observing, add a new observation. We can look it up. I think I already have it loaded, but so I was trying this out ahead of time, but I'll just go through the steps again. NGC 3201. Oh, I typed in NCG. NGC 3201. Okay, found it. It's loading a preview. And a preview usually comes up fast, but if it's slow, it's usually a problem with our server to the DSS, not on our side. And we see that occasionally. I'm seeing that right now. But it doesn't matter. And here we have observation name. They can, of course, change that as they want. And we have the recommended defaults, the lab, minus 12, 20, and up for at least half an hour is what we recommend. The advanced settings, we don't need that. And so you can see this is up in our Southern Hemisphere observatories. These are all Southern Hemisphere targets because the lab was built around our Southern Hemisphere telescopes. When we update the labs, we're probably going to change the targets to mid-latitude possibilities. But anyway, next you choose the filters. And this is described in the instructions coming down here. Now, the one thing I need to say is this is a pretty hefty observation. And it takes a fair amount of observing time. So we don't have each student do this. The idea is to put in one observation for the entire class. Now, I'll probably streamline this a little bit as I update the lab. I don't think we need to make this many observations to pull it off. But so the instructor would put this in, or a student would come up and put this in. You just have to make sure there are enough credits in your account or their account, and you do it for the whole class. Anyway, for this, we're looking in the V-band filter. I already have it marked here because I practiced it beforehand. And we do that because in these, there are reference stars, and the reference stars are calibrated in the V-band. And so we have to make our observations in the V-band as well. So selecting all the telescopes that have the V filter, and then I have more telescopes than are currently available to the students, and these are the ones I have with the V filter. Again, Prompt 5 and Prompt MO are the good Southern Hemisphere telescopes, at least this semester. Things may come and go. Particularly once we move to Afterglow 2.0 and we can add our telescopes with the larger format cameras, you'll see a number of other options pop up. Anyway, we'll save this, Prompt 5 and Prompt MO, and our reference scope is Prompt 5. And the lab, going through the instructions, it says put in one 80-second exposure, which the Prompt MO is 120 seconds. And I have different time accounts. And then the big difference here is normally this will be unchecked. You'll check it and repeat this observation. The lab says 168 times. That's once an hour for 7 days. It's a little bit overkill. We did that originally because we only had scopes in Chile, and so we knew a good chunk of those 168 would be skipped. We've since changed how we do the scheduling. It will take everything. It will basically wait until your telescope is available, and then observe it, and then wait at least an hour before trying again. So when we update the lab, probably 50 exposures would be sufficient. So it's going to repeat this one 80-second exposure 50 times with at least 1 hour gaps between them, and also continue on next available telescope if interrupted. So it should hand off back and forth between Chile and Australia as long as the weather is good. And the other libraries, they have a period of less than a day. So that's why we're doing an hourly cadence. And we'll automatically cancel 1 month out, which is also a healthy thing. Save and continue. It goes to the checkout screen. Okay. Now I think when I set up your demo accounts, I gave you each half an hour. which may not be enough time for this. You may need a couple hours to do that. If you want to try it out ahead of time, just let me know. I'll give you some more credits. But when I set it up for your class, I give each of the students half an hour, and then I give you a handful of extra time. Okay. So that, I'll put that aside. We don't need that. And the idea is, do this in front of the students. At the beginning of lab, either before or after your pre-lab talk, say, okay, we're going to put in the observation for lab 5. We're going to just put in one set for the whole class and do it in front of them so they at least feel part of the process. And in this new grant that we submitted, and hopefully will be accepted, that's one of the things that we're going to study. We know that the students get excited about putting in their own observations. We're trying to see if they can also get that same excitement level out of a class shared observation. And we're testing different ways, where maybe one student or the instructor puts it in for everybody, or each of the students put in a little part. So that'd be something that we study from a pedagogical point of view if we get this funding. Anyway, back to lab 4. Okay. So we'll come back to standard candles next time. This lab is lab 4. It has 4 parts. You, of course, don't have to do all of these parts. The first part is manual, and the last 3 parts are Skynet-based and kind of repetitive, but repetitive in a good way, where they're repeating the skill and just solidifying in their mind by doing it over and over, but going farther and farther out in space each time. The first part is to use parallax to measure distance to objects on Earth. And then they're going to use parallax and Earth's diameter, which they measured in lab 2, to measure distances to objects within the solar system, be an asteroid. And I'll talk about how that's observed. Last time we didn't go through the process of putting that in because I said it's a little tricky. We're hoping to improve this. Right now, it pretty much has to be done by Skynet staff, but I'll come back to that. And hopefully once we get this funding, we'll make it such that everyone can do it, or at least the instructor can do it more easily than now. We also measure parallax to Venus to establish the astronomical unit. We then use parallax and the astronomical unit to measure distance to Alpha Centauri. Okay, so those are the goals: measuring parallax farther and farther out, calibrating the AU as we go. Equipment, protractor with attached string. We use this in the globe and lights version of lab 2, so you get to reuse it. A tape measure or a yardstick or something. You'll see you can have some flexibility in how to measure the distance in just a second. And computer connection for the Skynet stuff. 2 background sections. One is setting up the cosmic distance ladder, because that's a big theme moving forward. One of the things I emphasize is that distance is one of the most difficult things to measure in astronomy. Again, I know you all know the stuff that I'm presenting in these background sections. I'm just doing a quick version, give you an idea of how you may present it to a student or your students. But I like to drill in the fact that we can't see distance. It's always some trick to get distance. And here's just a standard example. These 2 stars appear to be the same brightness, but one is actually lower luminosity nearby. One's higher luminosity and far away. So just because something's brighter doesn't mean it's closer. We need some other trick, some other trick. There's a whole different variety of tricks, a bag of tricks, and that is what forms the cosmic distance ladder. And here's a pared down version. The cosmic distance ladder can be quite complicated. I went through it and extracted the most critical elements because we only have so many labs. And so again, in lab 2, we measure the size of the Earth by measuring the height of the sun at midday at 2 different locations on Earth at different latitudes. And in this lab, we have 2 more rungs: Earth baseline parallax out to an object like Venus to know the AU, and then we use the AU and stellar parallax to get to nearby stars. In lab 5, some of these nearby stars are Lyraes and Cepheids, and so we can calibrate them and then measure distances out farther. Again, the Lyraes are good for Milky Way distances. The Cepheids are good for nearby galaxies. Then also the type 1As to get farther out. And then in lab 8, we'll cycle back to Hubble's law, which uses the type 1As as well. In fact, we're planning a lab 9 multi-messenger astronomy using binary neutron stars detected by LIGO as standard sirens, which you can also use to measure Hubble's constant. So that will tie in a variety of ways as well. And that's built into a different grant that I put in as kind of the broader impacts component of gravitational wave follow-up. And we'll know about that come summer. Okay, so that's kind of a preview of what's to come. Now, parallax in particular, it's good to just start with this simple finger exercise. I tell my students to grab a finger, preferably their own, and put it in front of their face and close one eye and shift from eye to eye. If their finger's close, they see a bigger angular shift against the background wall than if the finger is far away. I'm sure you do this with your students when you introduce parallax in lecture setting. But this introduces some terminology. Baseline is the distance between observing points, in this case the two eyes. Of course, have the distance between the eyes and the finger, and then the angular shift. So in this lab, there are two types: Earth baseline parallax and stellar parallax, and the geometry is the same. Here we're on different sides of Earth, here we're on different sides of Earth's orbit. Here we're looking at the moon. So if you take simultaneous pictures of the moon from different sides of the Earth, it's a pretty big parallactic shift. It's about 2 degrees, or 4 moons, that it shifts between those two simultaneous images. And with stellar parallax, it's of course smaller. For nearby stars, it's about an arc-second, and of course it can be a lot smaller. But anyway, here's our favorite geometry. We saw this in Lab 2. We saw it, so in Lab 2 to measure the size of the Earth. In Lab 3, figure out the physical size of a planet. So we had a conversion between its angular size in arc-seconds, its physical size in AU, because we needed that conversion. So here we see it again in different contexts. So again, it's good driving in the same geometrical concept over and over. In this case, we have our baseline and the angular shift in the distance, and the angular shift is a fraction of 360. The baseline divided by 2 pi times the distance to the object. Whether it's Earth baseline or stellar parallax, again, the same geometry. So here's the same equation as always. Solving for distance, we have this, where theta has to be measured in degrees. I always want to emphasize that. Okay, so let's go through the procedure, beginning with the manual part. So again, you can skip this, though I like doing it. I think the students like doing it. On our campus, I have the south-facing observing deck. It's on a new building. It probably cost $1 million. It was meant for astronomical observation, but they never consulted any astronomers because it overlooks the athletic field and its bright lights. And they built up the north wall behind it high enough that you can't see the North Star. So you can't polar line telescopes, and it's pretty useless. But I do use it for this. It's south-facing. I have a number of objects that are fairly perpendicular to the wall, and it's a 90-foot deck, so it's nice. And this is how we do it. Again, there are the protractors and the strings. We have a nice straight wall, so the students get their eyes down at protractor level. We'll point to one of the two targets. We have a nearby target. The lab's built around finding a nearby target. In this case, it's the smokestack. And a far away target. In this case, it's the water tower. And again, you want it to be kind of perpendicular to your baseline because we're not going to get into doing it trigonometrically. Okay, and so they just walking through, the students doing the smokestack. They get their first angle, they walk to the other side of the deck, get their second angle, and both are pretty close to 90 because it's pretty perpendicular. Angular shift goes here. Then they get the tape measure and measure the distance between their 2 points. Now, being a 90-foot deck, I don't have a 90-foot tape measure, but I let them figure out what to do, whether they want to use the tape measure over and over again, or I bring up some yardsticks. The smart ones realize that the pavers on the deck are 2-foot pavers, and they just count the number of pavers. Anyway, I let them figure that out. They calculate the distance to the smokestack, and then I tell them it's 360 feet. Now, of course, you don't have access to my deck, so there are notes for the students at other institutions and also for the online students. At your institution, you'd want to find a similar setup. If you can't find one, you just skip this part of the lab. The online students, they each have to find their own setup, and they find smaller versions where they can measure the distance of the object. In this case, the smokestack, we measured it using Google Maps, but I don't assign that to the students, I just tell them. So at your institution, you'd find a place, and here they put the correct answer, which you provide for them, % error. Then they repeat it for the more distant object, and discuss sources of error. And the sources of error are consistency in how they position the string, which is really consistency with how they hold their head with respect to the protractor. If they get it wrong, it's fine as long as they get it wrong in the same direction for both measurements. That's a subtlety I don't test them on. If they say anything about difficulty positioning the string, I count that. Consistency with which they held the protractor flush against the wall, or if the wall isn't very straight, it's kind of rugged or something. Those would be sources of error. The precision of the protractor, it only has increments at the degree level, so some fraction of degrees the precision of the instrument. Those are the three primary ones. The really clever ones will say, well, if it's not perfectly perpendicular, you have to do some trigonometry. Or if you're picking an object that's really kind of close compared to the size of the baseline, also that involves trigonometry. We're making the equation we provided is small angle approximation. Most people don't get those other two sources of error, so I'm happy for, oh, and also difficulty measuring the baseline if they had to use their yardstick over, end over end over end. So there's 6 possible things that I could think of, and if they get any 3 of those, I'm happy. Then we have some questions that are designed to make them think a little bit. Which of their measurements was less accurate? Which should have been? The more distant one should have been, but we ask why. And the smaller the angular shift, the closer the angular shift is to the precision of the measuring device, that's where you're going to have your difficulty. Next question is for a fixed baseline. At what point does parallax cease to be an accurate measuring technique? Again, it's laying into that concept again. Once your angular shift reaches the precision of your instrument for a fixed baseline, that's as far as you can go. And finally, what are 2 ways that you can have more accuracy, better accuracy, and that's a more accurate angle measuring device or a bigger baseline? Okay, so that's the manual part. Pretty straightforward, but again, it's in a lab that's primarily computer-based. It's good to get the students to make a few manual measurements here and there, I think. Okay, observing an asteroid with Skynet. We skipped this last time because I said it's really too difficult to pull off unless you're Skynet staff. There are instructions for how to do it if you want to give it a try. This is an older version of Skynet, but basically you look at the air mass chart. You put an asteroid in, a main belt asteroid. You look at the air mass chart. You find Northern Hemisphere, North America observatories, and the Chilean observatory. And then you set a do not start before time. There's a place to do this in Skynet. And hopefully you have high enough, then it's about luck. Is the weather good at both sites? And are you at the top of the queue at both sites simultaneously? So once you hit that don't start before time, it runs on both telescopes. And what you're actually doing is doing a short sequence on both telescopes, hoping that you have at least some overlap. You need one image that's kind of overlapping or near simultaneous between the 2 sites. And it's just clunky. And part of the grant we put in is to find a way to, to build some more stuff into Skynet to make this easier to achieve. Until then, my staff goes out and does it every year or 2, and we post it to a common space. So not the final answer that I want, final way to do this that I want, but it's a start. Okay. Now, the upcoming sections are identifying the asteroid and measuring the distance to the asteroid, and this is all done within Afterglow. So let me load up Afterglow here. My password, same password as Skynet, of course. Again, this is the old Afterglow. And file, actually, okay, the instructions are written out in the lab. I'm just going to show you. You go to process and align. So the first thing we're going to do is make a movie. As I said, we did a rapid fire sequence. We take one of the telescopes, we take that rapid fire sequence, we're going to make a movie to figure out which point of light is the asteroid. If you're just looking at a single image, you don't really know. So add files, sample images, 101 lab, lab 4 parallax. And I was messing with this one beforehand, so I'll use it again. This was fall 2014. And so we have them in 2 directories, movie and parallax. When parallax, you have the 2 simultaneous images between the 2 observatories. movie, you have the rapid fire sequence from one of the telescopes. In this case, it's the Chilean telescope, prompt 1. So, but we have to align them first to make a movie, as you may recall from a previous lab. Okay. And so here we're in the alignment thing. I like to fit first. And we have 7 images here. And for this, since they're all from the same telescope, we can again do single star, 1-star alignment. And you can pick any point of light here. Now, if you pick the asteroid in your movie, the asteroid will be at the center and everything else will move. If you pick a star, then all the stars will be stationary and the asteroid moves. So it doesn't really matter if you accidentally align to the asteroid. It will still be clear. And you kind of want to pick something near the center because stars at the edge can come off. And here's a bright thing and kind of near the center. That's probably the asteroid being the bright thing. So maybe, again, you can align to it. I'll align to this because this looks more like a star to me. This is 1-star alignment. And again, it bounces around from image to image just because you can't point perfectly each time. Looks like the telescope's drifting over this sequence. Okay, select target directory, and it should load up the workspace. I select it. Next, and what it's going through and doing is it's aligning all the images to star 1, and it's saving just the intersection of those images because I selected intersection. Okay, that's done. And now we're going to go to Make Movie. This works just like you've seen before. And what was the name? That was Fortuna, I believe.
I thought it was Thisbe.
Thisbe, thank you. Let's see, Thisbe. Here's my Thisbe 0 through 6. Select. Next. It loads them in. If you have a slow connection, it may take a second. And now I'm going to play the movie. And it's clear which one is the asteroid. All the stars are stationary, and again, you can zoom right in. So now we know which one is the asteroid. Okay, so you're going to stop that. And then the next part, once you've identified the asteroid, is to measure the angular shift. So we're going to go back to alignment. We're going to add files. I'm still in the workspace, so sample, 101 lab, parallax. This was fall 2014, parallax. And so we have one of those images from prompt 1 and a simultaneous image that we got with Moorhead Observatory that's over top of me. Loading those 2. Now this is a little different. These are taken from 2 different telescopes. Let me get rid of the movie in the background. Don't need that anymore. Let me fit them here. So here's the Moorhead image. Doesn't go very deep, not as many stars as we saw in the Chilean image. There's the Chilean one, more stars, Moorhead. And I like to hop back and forth between them a little bit, kind of connect the stars between the 2 images. And this requires not 1-star alignment, but 2-star alignment, because different telescopes, you can have different plate scales, different rotation angles, depending on how they screwed the camera on. So you have to define 2 stars. So you start with the first image, and you want to pick 2 that are kind of well separated. If you pick 2 that are really close together, if you have any uncertainty, it becomes greater at the edges of the image. So I hop back and forth. I know that's the asteroid because we just determined that. You don't want to align to the asteroid. That's why we went through with the movie. So maybe this one and this one, let's just confirm it's in both images. Indeed it is. So I'm going to select the first star. Takes me to the other image, select it again. It says star 1 if you can't read it through the video cast. Select this one, star 2. Again, you're going to select a target directory, loads up the workspace, and now it's aligning the second to the first. And now we're going to go up to the overlay. Under process, we have align, make movie, overlay, and batch photometry, which we'll see in the next lab with standard candles. The overlay, and we're going to add the files from the workspace. Thisbe, let's see, Thisbe Moorhead, control Thisbe prompt 1. Next, and it's loading them in. And I'll fit. And there are two ways. There's a slide here. So here's the Moorhead image. Here's the Chile image, and I can go kind of halfway in between. I can also flicker between the two images. And so you see we lined the stars lined up really nicely, did the rotation and everything. But it's clear we have one of these things that has a shift between the two images. And that's this right here, the asteroid again. And this is not a shift due to the motion because these are simultaneous or near simultaneous. So this is a shift due to parallax from observing this asteroid from different sides of Earth. And we've done this, just manually all the way out to, I think you can do it out to Saturn if you're really careful. You can do it out to Jupiter. So just a side note, if you wanted to be more advanced in Lab 3, the one piece of information they had to look up from Stellarium was the distance to Jupiter. You could actually measure it through parallax. But anyway, that's a little bit higher level than what we're targeting here. Anyway, you zoom in. Now we're going to use the measuring tool. Again, they went through these exercises previously to learn how to use all the tools, primarily in Lab 1. And you get to the center of one of them, just kind of eyeball it and click. And this was a bit of a hack as we did this, so the arrow only appears in one image, but it's okay. Then get to the center of the other, click, and it says the distance between them is 5.44 arc seconds. So that's the parallactic shift. So back to the lab manual for a second. That's where we identified the asteroid. And again, movie downloads aren't working and won't work before we release 2.0, so don't worry about saving the movie. But here in measuring the distance, they record the angular shift here, 5-point-something arc seconds. Then they record the fraction of Earth's diameter between the two observing positions, because we're not exactly on opposite sides of the Earth. Here I have a table of distances to different northern hemisphere observatories from our site in Chile. They're all about 0.55 or so, 0.55. Here they entered the size of Earth they measured in Lab 2. This is just to remind them that these are connected. They measured the size of Earth before. Here they enter the true value. And we'll then use the true value so we don't accumulate errors as we go along the cosmic distance ladder. But I try to connect the labs saying, oh, you measured this in the previous lab, now we're going to bootstrap off it and get farther out. So this is just to remind them they measured the size of Earth before. Here they put the true value. Here they put 55% of the true value in this case, so the baseline. Then they can calculate the distance to the asteroid is the baseline over 2 pi times 360 over the angular parallactic shift, which they have to remember to convert to degrees. And they get a distance. And most main belt asteroids are in the 10 to the 8 to 10 to the 9 kilometer range. So if they have anything around there, they're good, and they can discuss their sources of error, difficulty selecting the center of the asteroid in each of the images when measuring the angular shift, their measurement being contaminated by the motion of the asteroid through space. The two images probably aren't perfectly simultaneous. And the other one is the more advanced one, that maybe our baseline isn't exactly perpendicular to the asteroid. It probably is because we went north-south on the planet, which is kind of perpendicular to the plane of the solar system, but we're tipped 23.5 degrees. And again, I don't want to bother them with trigonometry at this level. Though we do have one lab that we do talk about trigonometry, we just don't make them, well, we make them use some equations. That's a little bit later. But here, we'll just let that be a source of error. Okay, so that's the main belt asteroid. And we're going to do this 2 more times, once to Venus to establish the astronomical unit, and then to Alpha Centauri. So it's going to be the same thing over again. Now, here's a little bit of background with Venus. And this is, I do this calculation in lecture in the simplified form. In the lab, we do it in this slightly more realistic way. So here's Kepler's third. People observe the orbital period of Venus, 0.62. So using Kepler's third, you can figure out that it's 0.73 AU from the sun. We're by definition 1 AU. So at closest approach, there's a difference of 0.27 AU. So if you can measure the parallax of Venus at closest approach in kilometers, you know that 0.27 AU is that number of kilometers. And we do this in class. And it's like 1 arc minute of parallax at closest approach. Now, in reality, that doesn't work because you can't measure the parallax then because the sun is right there in the sky. So in lab, we take this 1 level up, and we're not going to measure it at closest approach, but we're going to use this image here, which is Venus. And from its phase, slightly gibbous, you can tell where in the orbit it was. It was somewhere over here because that's the only place that has that phase. And then we go through, we don't make them go through the geometry. We say, okay, when it's here, it's 1.34 AU away. Because we're going to give them a canned image. And the reason it's a canned image and they don't take it themselves is because often Venus is too close to the sun to observe. Sometimes it's not, often it is. But the other problem is Venus is so bright that if you don't want to saturate Venus, you have to do a short exposure, and you don't have any stars to align to. But if you observe long enough to have background stars to align to, you saturate Venus. And so what we tell the students, and I'll be honest with you, but I'll lie first, what we tell the students is we got these special filters made that are neutral density in the center, block out most of the light in the center, but leave the rest. So you can have background stars and an unsaturated Venus. Now these would be very expensive custom filters just for this lab exercise. So I purchased them from the Photoshop company. It's a doctored image, but they don't need to know that. And my postdoc did a really good job doctoring even the diffraction spikes and everything. So pretty good. Anyway, let's go to Afterglow and do this exercise. So again, we're going to align. Let's get rid of that there. Add files. Sample images, lab 4, Venus. Here they are, just select them both. And this is again 2-star alignment. I missed a step here. Let me try that again. Process, align, add files, select, next. Okay, there they are, fit. And yeah, 2-star alignment because it's taken from Moorhead and prompt. So I'll show you the 2 images. There's the prompt image, there's the Moorhead image. So you can see similar background stars between the 2 of them there. It's still on 2-star manual. So I want 2 stars that are kind of well separated. And so maybe this one and this one. Let's see if it's, yep, they both are in both images. Another one would be this one right here. Start with Moorhead. I'm going to select star 1. It's moved over here. Star 2. It's moved right to the edge of the image, but still should be fine. Target directory, workspace, next. So it's rotating and scaling those 2. And then back to the overlay tool. And the workspace, Venus, select, next, fit there. So if I flicker, you can see those background stars did line up real nice. The little dark region shifts, and Venus is shifting. So again, it's the ruler tool. And I've got about 8 arc seconds there. Okay, so you get the process. They enter their shift here. Same deal as before, fraction of Earth's diameter. And so what is the baseline? 55% of Earth's diameter. Calculate the distance to Venus, and that's in kilometers. And then we solve for an AU. 1.34 AU is that distance in kilometers. Divide both sides by 1.34, and they just measured the astronomical unit. Should be about 1.5 times 10 to the 8 kilometers. Calculate a percent error. And the sources of error are the same as before. Difficulty picking the centers, and it may not be exactly perpendicular. Last one, Alpha Centauri. And so before I do this one, I should say this lab is about a lab and a quarter. If I take all the students outside and do the manual observing, that of course takes some time to move the students around. But since the Skynet part is repetitive, and again, I argue repetitive in a good way. It's reinforcing the skill. If they do just one or two of them in lab, they should be able to go home and finish it up because it's the same thing over again. So again, here's our special neutral density filter, so we can see the Alpha Centauri system and the background stars despite their vastly different brightnesses. And I'll just go through the step again. Can't hurt for you to see it one more time. Align the image. Back up. Sample 101, Lab 4, Alpha Centauri. Select these two. Now these are taken 6 months apart. This is why, you know, they couldn't do Venus because of the reason, you know, other than the fake filter, you know, Venus being too close to the sun. Alpha Centauri, they can't do this because you observe it 6 months apart. That doesn't work in the lab setting, so it's also archival. And the asteroid's the part that's not archival. Next, fit. So these are taken with the same telescope, but over 6 months we've maintained the telescope. We've had to take the camera off and put it back on. So you still want to do two-star alignment because there could be a bit of a rotation. And in, you know, I'm hopping back and forth. I'm looking at this here and this cluster 3. It's here and it's up there. There's a little bit of a rotation. Make the star 1. I'll zoom in a little bit. So see, it does auto-centroid these, so you don't have to be perfect. And that's why I don't include this as one of the viable sources of error, because the alignment process is pretty robust. Make sure I did that right. 1 and 2, 1 and 2. Yep, got the right stars. Now, given that it does auto-centroid on the stars, as long as they pick the same stars in both images, it really shouldn't be a source of error. Now, if they, you know, sometimes they may not get the same stars in both images, and that's the kind of error that doesn't count as, you know, that's human error. So they got to go back and redo it. That's not a valid source of error. And they'll tell, because when they go to the overlay, they didn't pick the right background stars. The stars won't match up. Process, overlay, add files. See, these are Alpha Centauri, so here they are. So I'll flicker, oops, flicker, and you can see the background stars are staying put, so we did the alignment correctly. But if we zoom in here, we see that, so Alpha Centauri, it's a multiple system. It's a triple. I imagine A and B are, this is both A and B, and that's Proxima. Is that right? Does anyone know? Or is this A and B and Proxima someplace else? I can't I bet this is A and B too close together for us to resolve, and that's Proxima, but you may want to check. And sometimes students will try to measure the distance between them. That's not really the goal here. We want to measure this shift, so just focus in on one of them. And about 1.2, 1.3 arc seconds. So definitely measurable, but it's sub-blurring scale here, but definitely measurable. And then the lab just wraps up in the same way as before. You input your angular shift. We ask, what's the baseline? I never tell them. With stellar parallax, they should know the baseline is always 2 AU. And we have them convert this to kilometers because they just measured the astronomical unit. So I want to emphasize that now that you have that, it connects. So they put in their measurement of the AU and then the true measurement of the AU. Let's see, here they're converting to kilometers using their measurement of the AU. Here they're converting to kilometers using the true one. Again, I don't want the errors to accumulate as we march along the cosmic distance ladder. And then they can measure the distance to Alpha Centauri because they have the baseline, 2 AU in kilometers, and they measured the angular shift. Got to convert to degrees, or else they'll get the wrong answer, and it comes out in kilometers. We have them Google true answer in kilometers, calculate percent error, And these percent errors, they tend to be really small, a few percent. And the discussion of sources of error, same as before, difficulty picking the centers, and it may not be perfectly perpendicular. That's it. That's the parallax lab. Again, it's about a lab and a quarter, so you can decide whether you want to do the manual exercise. But I think redoing the Skynet part 3 times is good in terms of learning the technique, but also marching farther and farther out. They do it first on something they measured themselves or as a class, the asteroid. Then they do it on Venus to establish the AU, and then they use that to get to nearby stars. And the next lab we pick up from the nearby stars to do the Aureliaries and the Cepheids, which now the guys up there, that's genuine. It used to be that there's this other part, spectroscopic parallax, in the cosmic distance ladder between the two. But I knew that would be kind of disappearing with Gaia, so that's one of the things I decided not to do. And we'll go straight to parallax and then Cepheids and type 1a. Those are the main rungs of the cosmic distance ladder. Questions, comments?
Hey, Dan.
Yeah.
As a quick question, do you have a rule of thumb of how long the baseline should be compared to how far away the object should be for that first?
Yes, so I don't have a rule of thumb, but they shouldn't be similar. So I'd say at least 3 or 4 times the distance of the baseline is, well, let's see. I said that one's 360 and our deck is 90 feet. So that's, about 4 times. So yeah, that 3 times or so. Now, if they do less, it's just a larger percent error and something they can talk about in the percent errors. But it requires some smarts on their part because we gave them an equation and they'd have to know, well, that equation's an approximation.
Okay.
Anything else?
No.
Okay. Next week, standard candles.
Okay.
See you all later.
All right. Later.
Thank you. Thank
Thanks.
you. Bye.
Thanks, Dan.
My pleasure.
Bye.
Thank you.